Hello students, welcome back to my channel. So today we are going to do one more important topics related to series resonance, that is quality factor. And this is very frequently asked question. They ask about the definition of quality factor as well as this is important for the numerical point of view also. Okay, so let's go. So the very basic definition of quality factor is that Q factor can be defined as the ratio Q factor. Q factor that means Q factor is also known as quality factor. Okay, so quality factor can be defined as a ratio of inductive or capacitive reactance at resonance to the resistance of the circuit. So by the definition only we can understand what is going to be the formula for Q factor. So Q can be written as Q is equal to XL upon R, or we can say XC upon R. So this is very basic definition of quality factor, and these are the very basic formulas which we can use for calculating quality factor of any circuit. But if we want to go in depth, so there is one more definition and there are few more formulas for quality factor. So if you want to just uh, do only the definition of quality factor, so this is going to be sufficient. But if you want to go in depth, then you have to see some more part of this video. Okay. If they ask specifically for a series resonance circuit, then we will give this definition. If they ask quality factor of series resonance circuit, then you are supposed to give this definition. What it says the quality factor of series circuit is defined as the ratio of voltage magnification at resonance frequency. So one more thing I would like to tell you is that the series resonance circuit uh, gives magnification of voltage. That means amplification of, we can say amplification of voltage. Let's see if we are supplying V voltage and Vc or VL is going to be voltage across capacitor or inductor. So at resonant frequency, Vc or VL is going to be greater than V, that is your voltage supply. So basically the series resonance circuit is magnifying the voltage. So that is why this definition occurs, and how it is saying that magnification of voltage. So it is also known as magnification of voltage. So we can say Q will be VL upon V or VC upon V. As we know, at resonance frequency, that is F naught, Vc is going to be VL. So we can use either value of voltage, that is going to be same only. Okay, so this is one more formula for quality factor. Now we will derive few more formulas for it. There is one more very common use formula that we will derive again. So if it is Q is equal to VL by V, so at F naught, that is your resonant frequency, what we can write Q is IXL upon IR at resonance. Z is R, that we know. So this I will get cancelled out, and now we can put the value of XL, that is 2 pi F naught L upon R. Okay, and we know the value of F naught for series circuit, that is 1 upon 2 pi under root of LC. If we put this value, so what we will get, Q is going to be equal to 2 pi into 1 upon 2 pi under root of LC into L over here and R here. So what we can cancel? This, 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 and we will have under root of L. So finally we will have 1 upon R under root of LC. So this is one more formula for quality factor which you can use in the numericals. Okay, and you can try to derive formula for Q is equal to VC upon V. So that is your homework. I'm not going to derive this. You are supposed to derive. Okay, do it at home. Now this is all about the quality factor of series circuit. Now we will do one more important definition, that is selectivity. Uh, Selectivity is the term which define how that specific circuit is performing. So how we will define it? The sharpness of tuning of RLC series circuits or its selectivity is measured by the value of Q. I'll tell you how it works. Uh, First I will draw a response curve. This is your response curve for series resonance circuit. Okay, this is between F and I. This is known as response curve. Okay, so if quality of a circuit is good, then it will have a sharp curve like this. Okay, and if the quality of circuit is low, then it will have a flat curve like this. Okay, and if you have good quality, that is curve sharp curve will give you, I'm sorry, it is not looking good. Sharp curve means high quality, high Q factor and high selectivity. Okay, and for flat curve, for flat curve, low quality and low selectivity. So this is how, by knowing the quality only, we can tell how selectivity of that specific circuit is going to be. So that's going to be sufficient for selectivity. You should not go much detail in of this topic. Okay, so there is one more thing which is important, that is relation between the bandwidth. First we will understand what is bandwidth, then we'll come to relation between the bandwidth and selective this Q factor and resonant frequency. Okay, so first we'll understand what is bandwidth. Bandwidth is going to be the range of the frequency for which circuit will perform its work. That means supposedly if we are sending signal to particular area, so we are supposed to tune our transmitter for a range of specific range of frequency. So bandwidth tells us that what is the range of frequency for which we can tune our circuit. Again I am drawing a response curve for series circuit. Okay, so here we can easily see it that there is two frequencies. One is lower frequency and other is higher frequency of this range. So the range of this frequency will be known as bandwidth. And by knowing this, what we can say, the bandwidth of series resonance circuit is defined as the difference between the frequencies at which circuit power reduced to 50%. That is 50% of the maximum power. So we know that at resonance we get maximum power in series circuit. Okay, so here at F1 we will have max P max by 2, and here also we will have max by 2. So how will get, I'll come to know about the value of F1 and F2. F2, we will see where we are getting the half value of maximum power. So wherever we will get half value of maximum power at lower range, that will give you the value of F1, and where we will get half value of maximum power at higher range, that will give you F2. So that is how it works. Okay, I guess that is going to be sufficient for you. Now we will come to the last topic of this video, that is relation between the resonant frequency, quality factor and bandwidth. So we know what is bandwidth. Bandwidth is the range of frequency. So how it we know that bandwidth of circuit is going to be inversely proportional to the quality factor of circuit. Because see, if we have wide range, then we are supposed to we have to compromise uh, quality of the signals, that we know. It's a very general thing, right? So definitely if we have wide range of frequency, we will have bad quality of signals, and if we have a good quality of signals, then we are supposed to have narrow range of frequency. So that is how we can say that bandwidth is going to be inversely proportional to the quality factor. Okay, then if we talk about the frequency, then bandwidth is directly proportional to the frequency. That is your F naught. So we can say that bandwidth is directly proportional to this and inversely proportional to quality factor. So this is going to be your final formula for a relation between the resonant frequency, quality factor and bandwidth. Now I would like to conclude this, that if Q is increases, that is if quality factor increases, then bandwidth decreases, as these are inversely proportional, and making curve more sharp. We know if Q is high, then we will have sharp curve in our response curve, right? And if we have sharp curve, then definitely we will have high selectivity, that it will increase the selectivity. Similarly, if we reduce the quality factor, then bandwidth will increase. Definitely we'll have wide range of bandwidth, but our response curve is going to be flat and selectivity of the circuit will be low. Okay, so that's all about this. So let's conclude at this point what we have learned in this video. First, we have learned the formula for quality factor. That was a very common formula. That is XL by R or XC by R. Then we specifically learned the formula for series circuit, that is VL by V or VC by V. Then we derived a formula for quality factor, that is 1 upon R L by C. So these are the three formulas which we have learned in this video, and we have learned that bandwidth is inversely proportional to the Q and directly proportional to the resonant frequency. And if Q Q is high, we'll have sharp curve. I'm sorry, we'll have sharp curve and high selectivity. Similarly, if Q is low, then we'll have flat curve and flat curve and low selectivity. Okay, so that's all. I guess it will definitely help you out. Okay, thanks for watching this video. Bye.